Good morning, everyone. I'm Zoltán Lehóczky, and with my colleague Álmos, we would like to tell you a bit about how we created a high-level software implementation of a new floating point number type called Unums, specifically Unum Type 1 and Unum Type 3 called Posits. And at the same time, we have also created a hardware implementation with FPGAs using our own tool called Hastlayer. So let's see how all of this come together. Just a bit of introduction before anything else. We are from a company called Lombiq Technologies. As we have heard, there is no free lunch unless you are a GPU Day sponsored by Lombiq Technologies. We are, by the way, a Hungarian software services company. We mainly work with Microsoft technologies, specifically .NET, ASP.NET, and a web content management system called Orchard. We are based in Budapest, but actually all of our clients are foreign, mostly from North America. And our customers also include companies like Live Nation or Microsoft itself, or even institutions like the Smithsonian Institution. And when we are not doing web development, then we are doing some research and development, like with our Hastlayer project. The first shorter part of this talk will be me introducing Hastlayer, which will be a bit of a recap of last year's GPU Day even. And after that, the bigger part will be Álmos's about Posit and how it comes together with Hastlayer. Bit of warning before anything else. Hastlayer is pretty much in an alpha state still. So it works fairly well. We have some quirks to iron out. And our Posit work is also pretty much ongoing. So you can also check it out on GitHub. We'll show the links to every source code that we show today later. But that is pretty much ongoing as well. So let's talk about Hastlayer first. What is Hastlayer? Hastlayer is basically a tool that takes a computer program and creates an equivalent hardware implementation, an equivalent hardware logic out of it. So before we had a piece of software, now we have a piece of hardware. And not just any hardware, but we are actually using FPGAs. Who has worked with FPGAs here before? Raise your hands, please. Well, probably 1/3. For all the others, FPGAs or field programmable gate arrays are basically computer chips that can behave like any other computer chip, within limitations, of course. So they can be dynamically rewired on the fly to mimic how another piece of logic hardware would work. And because they are basically application-specific processors, or you can configure them to be application-specific processors, they can be very power efficient, and they offer a highly parallelized architecture as well. Because as long as it will fit, you can put as many parallel executors on the FPGA as you wish. So what Hastlayer actually does is that it takes a .NET program and creates an equivalent FPGA implementation of it. Talking about .NET, that's where you take a .NET compatible programming language and it is compiled into a common kind of bytecode called Common Intermediate Language. And since Hastlayer processes that common intermediate language, that means that we support, at least in theory, any .NET language. So not just object-oriented languages like C# or Visual Basic, but also C++, or also functional languages like F#, or even scripting languages like Python, PHP, or JavaScript even. So all in all, what we would like to have with Hastlayer is that we want to offer all the computing benefits of FPGAs to all of us software developers. So if you have a compute bound, the CPU bound application or algorithm, which is highly parallelizable, then with FPGAs you can get a substantial performance increase. And at the same time, you get this with a higher power efficiency, so you can compute more things with less amount of electrical power. And with Hastlayer, all of this is just software development as usual. So let's see how Hastlayer works and how you would work with Hastlayer. So now we'll switch over to Visual Studio, which is the .NET development environment most of the .NET developers use, not the only one. And what we see here is an example called the parallel algorithm. This is not something of a real-life application. This is rather, as the name also suggests, an example, and an exaggerated example of a massively parallel algorithm. It kind of shows what's especially suitable to be accelerated with Hastlayer and with FPGAs. And what this algorithm does is that it takes an input number and then starts some tasks here. Tasks in .NET are basically an abstraction over threads. So if you start a task like this, then eventually the .NET task scheduler will take a thread from the .NET thread pool and execute the code inside the task. Now, how many such threads or how many such tasks can run in parallel depends on the platform the application is running on. In this particular laptop, I have an Intel i5 CPU and a mobile one, which has 2 physical cores and 4 logical cores. So the hardware level parallelism we'll get here is, well, around 4. But we are actually starting 280 tasks here. 280 because that many will fit on this FPGA that I have here and that I will use for this demonstration. Because when we process this piece of code with Hastlayer, and when all of this will be turned into a hardware implementation, then these tasks will be also turned into parallel little executor cores. So on the FPGA, we will get actually 280 little cores all working in parallel. So on the FPGA, we will get a hardware level parallelism of 280, not 4, not 2, not 32. And what we do in these tasks here is fairly simple. There is a bit of conditional logic here, which is executed 10 million times. And then the result is returned back. Again, this is also up on GitHub, so you can check it out in detail and the other samples as well, if you are interested. And once we start the tasks, we also wait for all these tasks to finish. And once all of these tasks are finished, we sum together their outputs. And that sum will be the output of the whole algorithm. As you can see, nothing really too useful, but kind of illustrative of a massively parallelized application or algorithm that computes something in parallel tasks. And now let's start this. This is part of a small console application that I have prepared here, and now it will, now Hastlayer will execute this on the FPGA. So again, I have this FPGA here, which will be used now. This is a relatively small, slow, and relatively cheap development board. It's an Nexus 4 DDR. But it was readily accessible and comparatively easy to begin developing with. So that's what we started it. And Hastlayer, in the background, created the hardware implementation and executed this parallel algorithm on the FPGA 3 times. And here we have the results. The results are that all 3 times on the FPGA, it took around 300 milliseconds to run this code. And if you take a closer look, it was actually exactly the same amount of time, down to the 10,000th millisecond. Now, the reason is that, again, with FPGAs, we get an application-specific processor, so to say. So the execution time is also deterministic. There is no operating system, and there are no other programs running. It's just your logic on that chip, wired in. If we also take the latency between the FPGA and the host PC into account, so the communication round trip, then it was around 400 milliseconds. There's a bit of latency because we are using a slow serial communication channel, because this is what's available on this FPGA, but we are also working on supporting higher level, faster, bigger, and more expensive FPGAs with, for example, PCI Express communication. But even like this, on the CPU, it took around 6 seconds. So 400 milliseconds versus 6 seconds. The CPU was an order of magnitude slower. So this should give you a bit of an idea of what's possible with Hastlayer and with FPGAs. Although this was, again, just an example. And now I will hand over to Álmos after starting the preparation for his demo, because he'll use the same FPGA to show you how he can work with Posit as well. So, Álmos, up to you. And back here.
So we wanted Hastlayer to have some kind of floating point support, and instead of going with the traditional way of implementing the IEEE floating point standard, we actually got a tip from our colleagues here at the Wigner institution about so-called universal numbers, in short Unums. So instead of implementing the standard IEEE floating point standard, we went with Unums, which is another kind of floating point numbers, which are being developed by Dr. John Gustafson, who is an American professor at Singapore at the A-Star Research Center. And last year we have presented our work with Unum Type 1s, which were all about interval arithmetics. And now I'm going to talk a bit about Unum Type 3, which we also call Posits. And they aim to be a better version and, in fact, a drop-in replacement to IEEE floats. So let's talk a bit about first the IEEE floats. So what is the problem with them? Why do we need something better than them? Well, first of all, they are wasteful in a sense because, for example, in a 32-bit IEEE float, over 60 million bit patterns only mean not a number. So they are not assigned to any real value. And well, this is wasteful. This is about 0.4% of all of the bit patterns that we can use. So it's not an insignificant number either. And there are many special cases, such as these NANDs, or there is a negative zero in the standard, which needs some complex logic and strange rules. And there are also subnormal numbers, which are treated differently. So these things need complex logic, which needs more hardware, more silicon, and to handle, and it makes execution slower and less energy efficient. We could also argue that the value distribution of the IEEE float is not really user-friendly because, for example, in a 32-bit IEEE float, we have a dynamic range from 10 to the minus 38 to 10 to the 38, so really vast dynamic range. And across this dynamic range, we have 8 exponent bits everywhere and 23 fraction bits everywhere. So no matter the magnitude. This is the same for the values around 1 and for the very large magnitude numbers. So maybe we could come up with something better for our applications. And a big problem is we can have different results on different computers, in fact, with this standard. Because most computers use some kind of internal scratch pad, so to say, a larger register to store and accumulate intermediate results. And the size of these may vary according to the IEEE floating point standard. And the even bigger problem is that the programmer has no oversight over this. So when do these internal scratch pads get used and how big are they? We don't really know. So we can get different results on different computers with the same computations. And please, with a quick show of hands, show me who has ever struggled to make mathematics work with IEEE floats. Okay, so there are some of you. Please, after the talk, come to our demo table to talk a bit about that. So, what do Posits have to offer to these problems, as solutions to these problems? As you can see, this is how a Posit looks like. Well, it works kind of a similar way to a standard IEEE float in the sense that we have a sign bit here, and we have a fraction here, and then we have a part, the regime and the exponent bits together, that tell us the scale factor. So the regime and the exponent bits together tell us where the binary point goes. And as you see, there are no fixed number of fraction bits and no fixed number of regime bits here. So let's see from right to left how these things work. Let's start with the fraction. Well, the fraction bits are just fraction bits, and the difference between Posits and IEEE floats is that we don't have a fixed amount of fraction bits here. So any bit that is left after the regime and the exponent is going to be a fraction bit, if there is any left, in fact, because the regime can take up all of the number. And another difference is that we have a hidden bit here, but it is always 1. So it's a great simplification. We don't have subnormals in the Posit system. So let's go with the exponent, where the exponent, there are actually 2 values that define a Posit environment, and one of that is the total number of bits, so the length of a Posit, and the other one is the size of the exponent. So this is fixed, or at least the maximum if it is fixed, because the regime can take up all of the bits. But so here in this example, the maximum of the exponent size, which I will call exponent size from now on, is 3. And the exponent works like an unsigned integer. So it can represent values from 0 up to 7, because we have 3 bits now. And so this is a very small scale, so it has to work together with the regime bits to tell us the scale factor and where the binary point goes. And the regime works the following way. It is coded in a unary way. So we just get the first regime bit, see whether it's a 1 or a 0, and see how many consecutive bits of the same kind we have until we find an opposing bit. So in this example, the first regime bit is a 0. We see that there are 3 zeros before a 1. So the value of the regime is going to be 3, or in this case, a negative 3, because we counted zeros. If we would have counted ones, then it would be a positive number. So that's how it works. And what do we do with this negative 3 now? We take the first value that cannot be represented by the exponent. So in case of a 3 with exponent, the first value we cannot represent with it is 8. And we multiply this negative 3 by 8. So we get a negative 24, which means according to the regime, we would have to shift the binary point to the right by 24. But then we also add the exponent, so we shift it back by 5 places. So altogether, we shift the binary point to the right by 29. So this is a bit tricky, so I have a nice intuition for you to show how it works. So let's imagine that you are at the ground floor of a building with a precious binary point in your hands, and you have to take it to the appropriate level. But this building has the same amount of floors below ground and above ground. And to take it to the appropriate floor, you have an elevator, that would be the regime, that only stops at every 8th floor. And you also have stairs starting from every floor that has an elevator access. But on the stairs, you can only go upwards, and you can only go upwards for 7 floors. So there is no way to reach another level with an elevator. So now you have only one way of reaching each floor. So that's how the regime and the exponent bits work together. The regime would be the elevator, and the exponent would be the additional stairs. So you have to go to the floor below your desired floor with the elevator, and then go up the stairs if needed. That's how you get where the binary point goes. And there is also a sign bit. And just to break the suspense, this is what this value actually is. So there is a sign bit. If it's 0, then the number is positive. And there is another thing that in practice we decode negative values in a following way. If the sign bit is 1, then we take the 2's complement of the rest of the number and just decode it as if it were a positive number. So what are the advantages of this fuzzy solution? Well, this is a very small 3-bit POSIT environment. We only have a sign bit and 2 regime bits here, in fact. And there are a few things I would like to point out about all of these values. First of all, there is only a 0. There is no negative 0 in the system. So that is nice. And another thing is that on the top we have a strange value that's plus minus infinity. So in the POSIT system we only have one value to represent plus and minus infinity, and in fact this also means not a number. So this works like a quiet NAND. And the reason that this is enough for us is that POSITs never underflow to 0 and never overflow to infinity. So if we get a calculation that's going wide, and our result would be much better, much bigger than the largest representable POSIT, then it will just stick with the largest representable POSIT. So that's largest representable POSIT also works kind of like an indicator that our result would be a very large finite value. But if we have an infinity, then it just sticks there. And there are also 2 kinds of symmetries on this picture that are very nice. First of all, it's symmetric from left to right. So every POSIT has an exactly negated counterpart. And the negation is a very easy operation. We just take the 2's complement of the POSIT. So that is nice. And from bottom to top, we see each POSIT's reciprocal on the opposite end. And all powers of 2s has exact reciprocals in the POSIT system. So here is a bit larger POSIT environment with 5 bits now. So you can see that the bits are color-coded here. The yellow and brown ones are the regime bits. The blue ones are the exponent bits, and the black ones are the fraction bits. And the things I would like to point out about this, as you can see, the values are much more tightly spaced around the value of 1. And as we go to larger and smaller magnitude numbers, we are jumping more and more in magnitude. So why is this good, and what makes this happen? Well, this happens because around the value of 1, we have only 2 regime bits here. So we have fewer regime bits, which means we have more space left for the fraction. So not only are these numbers more tightly spaced, they are represented with more precision here. So, and that is nice because actually, if you think about a 32-bit environment, but even in this environment, half of the POSIT values, we have the maximum number of fraction bits. And another quarter of them, we have 1 less. So in a 32-bit environment, you will have 27 fraction bits for half of the values, and then 26 for another quarter of the values, and then 25 for another eighth of them, and so on, which is a really nice advantage over the 23, constants 23 of the IEEE floats. And also, the most fraction bits, we have the most fraction bits where we need them the most, so around the value of 1, where most computations occur, and we are losing fraction bits when the magnitudes are getting ridiculously large or ridiculously small. So this is another example of that. This is the distribution of POSIT values. Each color stick represents a POSIT in an 8-bit environment, and the gray sticks are float values of an imaginary 8-bit environment. And as you can see, the values are more tightly spaced around 1, so there are much more POSITs around 1 than there are floats. And but even like that, the dynamic range of the POSITs manages to be larger, and also the dynamic range is symmetrical, unlike with floats. So these symmetries are important because of closure under different operations. So if you do operations like addition with POSITs, you have a larger chance of getting a result that is in the system, so an exact result that is representable by a POSIT, or you are probably getting a result with a smaller error. So another nice feature of the POSITs is that they have the quire. The quire is an internal scratchpad for computations that is required by the standard, and the programmer has oversight of when it gets used. So for example, with 32-bit POSITs, the quire is a 512-bit long register, and it is large enough so that each 32-bit POSIT, or in fact a square of the largest 32-bit POSIT plus the square of the smallest 32-bit POSIT can fit in it comfortably and perfectly exactly in a fixed point manner. And there are also carry bits, so we can accumulate those large and very small values several times and still get a perfectly accurate result if the programmers want this to be. So it is very useful because, for example, if you want to compute a fused multiply addition, then you can do this by taking the results, exact results of each multiplication, putting them into and accumulating them in the quire, and then only rounding the result back into a POSIT at the very last step. So by differing rounding, we can manage to avoid the rounding errors. And because the programmer has oversight over this and is required by the standard, it makes results consistent across platforms and across different systems, because every system will need to have it. And it also makes algebra work, like it makes the distributive and associative laws of algebra hold, or at least hold better, so it's very good for parallelization. Just to recap, what are the good things about POSITs? We hope that with POSITs you can use fewer bits to store the same information in a way that you can take a calculation that you used to have 64 bits floats to compute, and now you can do the same calculation with 32-bit posits and still get a result that is accurate enough. Or you can preserve your number of bits and get a more accurate results. And of course, it is very important for speed because most of our computations today are memory bound. So if you can reduce the number of bits in a computation, then it could get significantly faster. And of course, this also affects energy efficiency. And with posits, each way uses the same logic. So if we implement them in hardware, we can make simpler hardware, less silicon, cheaper, faster, and it can also be more energy efficient because of that. And it's very important that you get consistent results across platforms and with parallelization. So there is an internal arithmetic counterpart to posits, which are valids. I won't really go into that now, but valids consist of a pair of posits, and it has an advantage above traditional internal arithmetics that at the end of each posit, as if each tile, there is a u-bit, an uncertainty bit, which tells us whether the given end of the interval is open or closed. So it has some nice consequences in interval arithmetics that we can track that. So where can you get it and try it out? There are various open source implementations in multiple languages, and we have also made a .NET C# implementation. And we have also transformed our code to FPGA logic with Hastlayer. So now posits run on our FPGA board. So now I would like to talk about our posit implementation and our research results, because we have also presented an implementation at the Conference of Next Generation Arithmetics in Singapore. And we have a white paper published there. So what I'm going to show you is going to be a sneak peek into our research. And you can check for the details online. It's published online. I will show you the link at the end. So our implementation is, it's a 32-bit version. It uses unsigned integers as an underlying structure. We got addition, subtraction, and multiplication working so far, so work is ongoing. And we also support the quire and fused operations, such as fused addition and fused multiply add. And we have made some performance measurements. Our benchmark test was performing 100,000 additions both on the CPU and on the FPGA board. And you can see the speed results down there. So about 7.7 million posit operations per second on the CPU and about 500,000 on the FPGA. Well, keep in mind that this is managed code we are talking about here. And when comparing the speed of the two devices, well, first of all, these additions were not parallelized yet, and that's what the FPGA really excels at. And also, our FPGA board has a clock speed of 100 megahertz, while the CPU we tested on had 32 times that clock speed. So it makes sense to perform the clock cycle efficiency of the devices. And now we get that it took about half as many clock cycles for the FPGA to perform an addition than it took for the CPU. So we think, so it was about twice as efficient per clock cycle. So we think this is roughly parallel to the power efficiency of these devices. And we have also made a parallelized performance test, which is more interesting. We have performed 500,000 additions in parallel this time on 5 threads, 100,000 on each thread, of course. And as you can see, the FPGA took exactly the same amount of time in parallel to perform these 500,000 additions as the 100,000 before. But the CPU got somewhat slower because we wanted it to execute on 5 threads and it only has 4 physical cores. But on the FPGA, on the other hand, we can have as many little physical processing cores, so to say, as we want. So that's why it didn't get any slower. And you can see the speed of the FPGA got exactly 5 times faster. So now we have almost 2.5 million posit operations per second. And if we compare the power efficiency of these devices now, you can see that by both devices got more efficient, the FPGA got exactly 5 times more efficient. So it is now 4 times more efficient than the CPU with parallelization. So we are also planning to implement all of the other operations to make up for a fully functional posit library that you can use in all kinds of computations. We are also going to make 8, 16, and 64-bit versions with code generation, and we will also implement valid arithmetics in the future. So now let me show you how these posits work. Just a second of preparation. So what we are going to do here involves the quire, because we are going to calculate a fused sum. So we are going to take a bunch of numbers, add them together in the quire perfectly accurately, and then only do the rounding at the last step. And the input of this operation is going to be an array with 201 posits in it, and this is going to be the first posit. And this is a very special one because every single integer that is positive integer that is smaller than that can be exactly represented with 32-bit posits, and including this one. But the next representable number is this plus 2. So the next integer is not representable. So what would happen if we added a half to it? Well, with floating points and also with posits without the quire, if we added 200 times sequentially, each time a half to this number, and then see the result and give a half again, then we would get the original number back, because this half is not close enough to the next representable value, so we would always run back to the value we started with and get a nonsense result. But if we accumulate in the quire, we can avoid this trap. So let's see how it works out. Just a second. It has already run on CPU. And as you can see, we got an exact result. It is bigger by 100 than the original number, which is what we would expect if we had 200 times a half to something. And now we are waiting a bit for the hardware generation. And now it has also run on the FPGA. And as you can see, we also get the correct result. And on hardware, it took 66 milliseconds. While in software, it took 17 milliseconds. So actually, this was slower on hardware, but this is because we didn't use parallelization here, and this algorithm was sequential and really not the kind that is really suitable for FPGA. So this demo was more about the accuracy that we could gain. And so that's it about fused operations. And well, if you would like to find out more about Hastlayer or Posits or our research, then please visit the links above. And thank you for your attention. I believe we have a few minutes left to start a little discussion, so please ask questions. And after the presentations in the coffee break, you can visit our demo table at the back. So thanks.
Thank you very much. It's a big problem with the IEEE floating point implementation is that the fractional bit and the mantis are not aligned on a byte boundary, which makes data compression a hard problem. So can this be solved with posits?
Excuse me, could you repeat the part of the question? What's the problem with the IEEE floats with the mantis?
So the problem is that the fraction bit and the mantis are not aligned on a byte boundary. So if you want to compress the data and store it on the disk, for example, then you have to move around the bits, which is very expensive in certain applications. So could this be solved with posits? So can you force a byte alignment of the fractional bits and the region and exponent bits?
I think not really, because as you can see, there is not even a constant number of fraction bits here. So some posits may have 27 fraction bits and others may have none. So alignment is really difficult here. That's not really what posits are for. But they are in fact, I think, are already in a compressed form compared to IEEE floats. So if you see what values you usually use in computations, then maybe you can switch out your 64-bit floats to 32-bit posits and get the same accuracy.
Okay, further question?
Just one thing to add here. That being said, we haven't talked about that, but we also have implemented what we call a universal, a configurably sized Posit implementation, which I believe is also part of the standard. So basically, you can create as big Posits as you want for your specific application. And by the way, with Hastlayer, that will be also hardware implemented. So if that is that you are going to optimize for, you can create a Posit environment that will be optimized for that.
So you can even create Posits with like 9 bits length and 2 bits of exponent size, and any size you want.
Okay.
Do you make some comparison about the area requirements of the Posit adder and the standard Xilinx floating point adders?
Well, we haven't, because then we would have to implement IEEE floats too, and we had to choose between them. So
it would be interesting to see how larger.
I think there is some research going on about this, and the results are promising. So it is possible that Posits are going to be smaller in area, but you can look at posithub.org. So that's the epicenter of all of the research going on about Posits now, and you can find all the published papers there.
There is a yet unpublished white paper that we can't talk about yet, but which will be published in, I would guess, 1-2 months, that also elaborates on that. It's not by us, but you will be able to check out the hardware implementation details out there.
Okay, thank you.
We have still time for a short question.
Two very short questions.
So I have a short question about the Hastlayer. So as you showed us that it is capable to compile the .NET code from the task parallel library, and my question is that as most of us know that there is implementation for asynchronous patterns in .NET since .NET 4.5, and is Hastlayer capable to translate the code from the asynchronous finite state machine that it compiles to?
Generally, Hastlayer doesn't support all the C# or all the .NET features, and that is one of them. That with task.wait, wait all is currently the only pattern here that we support. Actually, the reason behind that was that at the time, ELSpy, what we are using for the decompilation of the .NET DLS, wasn't supporting that properly. It does now, so eventually we also support that.
Thank you.
The very last question.
Another problem with floating points is that they don't support associative and commutative operations for addition, for example, which means that when you perform unsequenced computation, you can get indeterminate results when you get the answer back. Is that what you were talking about with the internal scratch pad, or is that something different again that Posits also can mitigate?
That is what the quire is all about. So the quire has with that. Of course, commutativity holds without the quire too. So that is just natural. But for associativity and distributivity, you need the quire. But with the quire, you can achieve similar results and parallelize any way you want. And those properties hold.
Thank you.
Thank you.
So let's thanks Zoltán and Álmos again, and you can find them during the whole conference because they have the desk at the back.